For generations, movies, novels, and futuristic visions have quietly trained us to believe that traveling to other stars is just a matter of time. That if we build stronger rockets, smarter computers, and more powerful engines, we will one day cruise between solar systems the way airplanes cross oceans. But there is an uncomfortable truth that almost no one wants to confront. Interstellar travel is not just difficult. It is not merely expensive. It is not even limited by today's technology. It is blocked by the deepest laws of physics themselves. The universe has placed a hard wall between us and the stars, and no amount of optimism can remove it. When scientists talk about something being impossible, they do not mean hard or not yet. They mean something far more severe. They mean forbidden in the same way that perpetual motion machines are forbidden, in the same way that moving faster than light is forbidden. These are not challenges waiting for better engineering. They are limits written into the structure of reality. And after decades of studying relativity, quantum mechanics, and cosmology, this conclusion becomes unavoidable. Human beings are effectively confined to our own solar system. That idea feels emotionally wrong because the night sky looks so inviting. With modern telescopes, we have already identified thousands of planets orbiting distant stars. Some of them are roughly Earth-sized. Some of them orbit within habitable zones where liquid water could exist. From a distance, they feel close. But physically, they might as well be in separate universes. The first barrier is distance, and it is far more extreme than most people realize. The nearest star system, Alpha Centauri, is about 4.37 light-years away. That sounds small until you translate it into human terms. Light, the fastest thing in the universe, takes more than 4 years to make the journey. In kilometers, that distance is roughly 41 trillion. If Earth were shrunk to the size of a grain of sand, Alpha Centauri would be about 40 kilometers away. On that scale, even our entire solar system becomes microscopic. Our fastest spacecraft ever built, Voyager 1, is moving at about 17 kilometers per second relative to the Sun. At that speed, reaching Alpha Centauri would take roughly 75,000 years. That is not a rounding error. That is longer than the entire history of civilization. And Alpha Centauri is just the closest star. Most of the interesting planets we have discovered are hundreds or thousands of light years away. Some of the most Earth-like worlds we know would require millions of years to reach at Voyager's speed. So the obvious response is that we simply need to go faster. But this is where physics becomes merciless. If we want to make the trip to Alpha Centauri in a human lifetime, say 50 years, we would need to travel at about 10% the speed of light. That is 30,000 kilometers per second, nearly 2,000 times faster than Voyager. At those speeds, the energy required becomes enormous. Kinetic energy does not scale gently with speed. It increases with the square of velocity, and at relativistic speeds, it grows even faster. Even if we imagine a tiny spacecraft, perhaps 1,000 kilograms, barely large enough for one person and minimal life support, the energy needed to push it to 10% of light speed is around 450 quadrillion joules. That is roughly the energy that all of human civilization produces in nearly an hour. And that is just to speed up. When you reach the destination, you have to slow down. That takes the same amount of energy again. So now we are talking about nearly 2 hours of total global energy production for a spacecraft with the mass of a small car. This already reveals something crucial. Interstellar travel is not blocked by clever design or better materials. It is blocked by energy. The universe demands a staggering payment for moving mass at relativistic speed, and it does not accept our use. Even if we ignore fuel for the moment, we already see that sending people to the stars requires diverting a meaningful fraction of all energy produced by civilization just to move a single, tiny vehicle. That alone makes it clear that interstellar travel is not a practical extension of spaceflight. It is a completely different category of challenge, one that collides head-on with the fundamental limits of nature. And this is only the beginning of the problem. Because once we add fuel, engines, shielding, and human survival into the equation, The numbers explode in ways that quickly move from difficult to absurd. In the next part, we will see how even the most powerful fuels imaginable struggle against the brutal arithmetic of the rocket equation, and why chemistry, nuclear power, and even fusion fail to free us from the tyranny of distance. Now let's bring fuel into the picture, because this is where the dream of interstellar travel really starts to collapse under its own weight. Energy by itself is not enough. You must carry that energy with you, and carrying energy means carrying mass. And once you do that, you fall directly into one of the most unforgiving formulas in all of physics, the rocket equation. Chemical rockets, the kind we use today, are spectacular for reaching orbit, but they are laughably weak for interstellar travel. The energy density of even the best chemical fuels is tiny compared to what relativistic speeds demand. Hydrogen and oxygen, the most efficient rocket fuel we know how to use, releases only about 13 million joules per kilogram. Gasoline does a bit better, but it is still microscopic compared to what is required. To push a 1,000-kilogram spacecraft to 10% of light speed requires around 450 quadrillion joules. If you tried to get that energy from chemical fuel, you would need tens of billions of kilograms of propellant. That is tens of millions of tons of fuel for a payload smaller than a small car. And that is before you account for the fuel needed to slow down at the destination. But rockets do not just burn fuel to push the payload. They must also push the fuel itself. This creates a vicious exponential spiral. The more fuel you add, the heavier the rocket becomes. The heavier it becomes, the more fuel it needs. This is why the rocket equation is so brutal. When you run the numbers properly, chemical rockets cannot even come close to relativistic speeds. The required fuel mass quickly becomes larger than the mass of planets, then stars, then entire galaxies. In other words, chemical propulsion is ruled out by mathematics alone. So what about nuclear power? Nuclear fission releases about 1,000,000 times more energy per kilogram than chemical reactions. Nuclear fusion, the process that powers the sun, is even better. In principle, fusion can release hundreds of trillions of joules per kilogram of fuel. That sounds promising. On paper, a fusion-powered spacecraft could reach 10% of light speed using only a few tons of fuel instead of billions. But paper does not build spaceships. Fusion energy must be converted into directed thrust. That requires an engine. Fusion reactors need powerful magnetic fields, cooling systems, radiation shielding, and structural supports. Even if we imagine dramatic breakthroughs, the reactor will always be much heavier than the fuel itself. And every extra kilogram of engine requires more fuel to push it, which requires more engine mass to control it, which requires more fuel again. The spiral returns. Radiation makes this even worse. Fusion produces intense neutron radiation that would be lethal to humans. To survive, the crew compartment would need thick layers of shielding made from water, polyethylene, or other dense materials. This adds tons of mass, and that mass must be accelerated and decelerated along with everything else. Even under wildly optimistic assumptions, perfect efficiency, minimal structural mass, and miraculous engineering, the fuel fractions required for a human-rated fusion starship become enormous. You are no longer carrying mostly people and equipment. You are carrying mostly fuel and radiation shielding just to protect the people. And even if you somehow solved all of that, there is another invisible enemy waiting for you in interstellar space itself. Between the stars is not empty. It is filled with hydrogen atoms and microscopic dust grains. At everyday speeds, these particles are harmless, but at 10% of the speed of light, they become deadly projectiles. Your spacecraft would be plowing into trillions of hydrogen atoms every second. Each one strikes with enough energy to damage materials and generate heat. Over time, this bombardment would deposit megawatts of power into the front of the ship. That heat has to go somewhere. It erodes surfaces. It creates radiation. It demands even more shielding and cooling. And hydrogen is the easy part. Interstellar dust grains are much worse. These particles are tiny, often weighing less than a grain of sand, but at relativistic speeds, mass does not need to be large to be destructive. A microscopic dust grain hitting a spacecraft at 10% of light speed carries the energy of an explosive. Over a multi-decade journey, the ship would encounter millions of such grains. Each impact would punch holes, vaporize material, and generate lethal radiation bursts. To survive this, the spacecraft would need thick armor, electromagnetic deflectors, or massive sacrificial shields. Every solution adds more mass. More mass means more fuel. More fuel means more energy. The loop never ends. This is what makes interstellar travel different from all other forms of exploration. You are not just fighting gravity. You are fighting the structure of space itself. The faster you go, the more violent the universe becomes. And we have not even discussed time yet, the most subtle and cruel barrier of all. In the next part, we will see how relativity turns long journeys into paradoxes, how waiting becomes more rational than launching, and why even near light speed travel cannot save human exploration. Even if we imagine that we somehow solve the fuel, shielding, and propulsion problems, interstellar travel still runs into another wall that no engine can break through: time. The universe is not just large. It is slow. And when you try to cross it, time itself becomes an obstacle. A journey to Alpha Centauri at 10% of the speed of light would take about 44 years from Earth's perspective. That means anyone who leaves is committing to being gone for half a century. That is already more than most people's working lives. But it is worse than that, because the people they leave behind will continue to advance. Technology does not stand still. If humanity could build a starship that reaches 10% of light speed by the year 2100, it is extremely likely that by 2150 we would have better propulsion, perhaps 20 or 30% of light speed. That creates a strange paradox. If you launch today, you will almost certainly be overtaken by a faster ship that leaves later and arrives earlier. This is called the weight problem. From a rational standpoint, it is always better to delay your launch until better technology exists, unless you are already operating near the absolute limits of physics. And the absolute limit is the speed of light. To make interstellar travel truly practical, you would need to approach light speed closely. At 90% of the speed of light, relativity begins to significantly slow time for the crew. Years on Earth become months on the ship. From the crew's perspective, Alpha Centauri could be reached in a couple of years. That sounds promising until you look at the energy required. At 90% of light speed, the relativistic kinetic energy of even a tiny spacecraft becomes staggering. A 1,000 kilogram ship would require nearly 60 exajoules of energy just to accelerate. That is roughly 10% of all the energy produced by humanity in an entire year. And then you need that same amount again to slow down. Fusion fuel, even under perfect efficiency, would require tens of tons just to push 1 ton of payload. But that fuel must be carried from the beginning, which means you must also accelerate the fuel that you will later burn to decelerate. Once again, the rocket equation takes over and drives the mass upward until it becomes absurd. And at 90% of light speed, interstellar space becomes a war zone. Hydrogen atoms strike with hundreds of thousands of electron volts of energy. Dust grains become relativistic bullets that explode with the force of high explosives. The front of your spacecraft is being blasted by radiation equivalent to a small nuclear reactor. Shielding thick enough to protect the crew would weigh thousands of tons. That shielding would need fuel. That fuel would need more fuel. Even if you survive the trip, you face one final problem: stopping. If you do not slow down, you will fly through the target star system in hours. You will not be able to orbit. You will not be able to land. You will simply pass through and disappear into deep space forever. To slow down, you need to burn just as much energy as you use to speed up. And that energy must be carried with you from the start. Some have proposed collecting hydrogen from space and using it as fuel. This is the famous interstellar ramjet idea. It sounds elegant. Scoop up interstellar gas, burn it, keep going. Unfortunately, when physicists ran the numbers, they found that the drag created by collecting the gas is greater than the thrust you gain from burning it. The ship slows down instead of speeding up. Other ideas use giant laser sails, pushed by Earth-based lasers, then slowed down by stellar winds at the destination. These are clever on paper, but require absurd infrastructure. Lasers with powers comparable to entire national power grids, mirrors thousands of kilometers across, and perfect control over light years of distance. This is no longer engineering. It is fantasy. But suppose, somehow, we did it. Suppose we had a ship that could reach another star in a few years of ship time. Could humans actually survive the journey? That brings us to the most unforgiving barrier of all, biology. In the next part, we will see why, even if physics allowed interstellar travel, the human body almost certainly does not. Even if we imagine that some miracle of engineering allowed us to build a starship capable of surviving the journey between stars, we still face a far more fragile obstacle: ourselves. The human body evolved under very specific conditions: Earth's gravity, Earth's atmosphere, and Earth's magnetic field. Strip those away, and our biology begins to fail. Beyond Earth's protective magnetic bubble, space is flooded with radiation. Not the gentle kind that warms your skin, but high-energy particles fired from exploding stars, black holes, and distant galaxies. These galactic cosmic rays consist of fast-moving protons and heavy atomic nuclei that can tear through spacecraft walls and through human tissue. They damage DNA, destroy cells, and increase the risk of cancer, neurological damage, and organ failure. On the International Space Station, astronauts receive about 50 times more radiation per year than someone on Earth. For missions lasting 6 months or a year, this is considered acceptable, though still risky. But an interstellar journey would expose astronauts for years or decades to far higher levels of radiation, especially outside the sun's protective heliosphere. Even a short 5-year journey could deliver radiation doses high enough to dramatically increase cancer rates and cause long-term damage to the brain, eyes, and immune system. The only real way to block this radiation is with mass. You need thick layers of water, plastic, or metal to absorb the particles before they reach the crew. But this shielding weighs thousands of kilograms per person. And every kilogram of shielding must be accelerated, decelerated, and protected from interstellar dust. We are once again trapped by the mass and energy problem. Gravity is another enemy. In microgravity, the human body rapidly deteriorates. Bones lose density at a rate of 1 to 2% per month. After a year, astronauts can have bone strength comparable to elderly patients with severe osteoporosis. Muscles shrink. The heart weakens. Vision problems develop as fluids shift inside the skull. Even with constant exercise, these effects cannot be fully prevented. To avoid this, you would need artificial gravity, usually created by rotating the spacecraft. But a rotating habitat must be large, typically at least 100 meters in radius, to avoid disorienting and harmful Coriolis effects. Building such a structure adds enormous mass and complexity. You need strong materials, bearings, motors, and rigid supports. Once again, the ship becomes heavier, which means more fuel, more energy, and more shielding. Then there are the psychological effects. Humans are not designed for decades of isolation in a metal tube. Even astronauts on the space station, who have communication with Earth and the ability to return home in an emergency, struggle with confinement, monotony, and stress. An interstellar crew would be years from Earth with no possibility of rescue. Conflicts, depression, and breakdowns would be inevitable. Some people propose suspended animation or cryogenic freezing. This is not science. Freezing human tissue causes ice crystals to rupture cells, destroying organs at the microscopic level. No technology exists to reverse that damage. Others suggest extreme metabolic slowing, similar to hibernation. Perhaps one day we might reduce metabolism by a factor of 10. But even that would only turn a 50-year trip into 5 years of conscious experience, still a massive burden on the human mind and body. This leads to the idea of generation ships, enormous vessels carrying thousands of people who would live and die during a centuries-long journey. Their children and grandchildren would arrive at the destination. But this is no longer physics. It is sociology, ecology, and human nature, all working against the idea. A generation ship must be a perfectly closed ecosystem. Air, water, and nutrients must be recycled with nearly 100% efficiency for centuries. Even the best experiments on Earth, like Biosphere 2, could not maintain stable balance for a few years. A small failure in space means extinction. Genetic diversity is another issue. A small population risks inbreeding and genetic disease. You would need thousands of people just to maintain healthy genetics. You would need a stable society with laws, education, conflict resolution, and purpose, all inside a vessel with no escape and no rescue. And what would be the reward? After centuries, they would arrive at a star system that Earth-based civilization has already explored with faster probes. They would be technological relics, stepping into a future that passed them by. The mass of such a ship would be millions of tons. The energy required to move it would be beyond comprehension. Generation ships are not engineering projects. They are fantasy stories. So if humans cannot go, what about machines? In the next part, we will look at robotic probes, the Fermi Paradox, and what the physics of interstellar travel really tells us about intelligent life in the universe. If humans cannot realistically travel between the stars, what about machines? This is where the picture becomes less bleak, but also more revealing. Robots do not need air, food, gravity, or radiation protection. They do not care about boredom, isolation, or time. For them, a 20-year journey is no different from a 20-second one. And that makes robotic interstellar probes not only possible, but likely. This is the idea behind projects like Breakthrough Starship, tiny spacecraft no larger than a postage stamp, pushed by enormous Earth-based lasers to a significant fraction of the speed of light. At 20% of light speed, such probes could reach Alpha Centauri in about 20 years. They would zip through the system, take images, measure atmospheres, and send data back to Earth before continuing on into deep space. This is breathtaking science. But it is not colonization. These probes cannot slow down. They cannot land. They cannot build habitats or create new civilizations. They are messengers, not settlers. This distinction matters because it leads directly to one of the biggest mysteries in science, the Fermi Paradox. The universe is unimaginably large. There are hundreds of billions of galaxies, each with hundreds of billions of stars. Many of those stars are planets. Some of those planets should have life. Some of that life should become intelligent. So where is everyone? One answer is that intelligent life is rare. Another is that civilizations destroy themselves. Another is that they are hiding. But physics offers a simpler and more unsettling explanation. No one can go anywhere. Every advanced civilization, no matter how brilliant, faces the same wall. The speed of light is universal. Energy scales the same way everywhere. The distances between stars are fixed. So civilizations may spread through their own solar systems, build massive structures, and harvest their star's energy, but they cannot leap from star to star. They are trapped by the same geometry and energy limits that trap us. In that picture, the galaxy is not empty because life is rare. It is empty because interstellar travel is impossible. Every civilization is an island. They may look out at the stars. They may detect planets and dream of them, but they can never reach them. That would mean the universe is full of life that is forever isolated, millions or billions of civilizations, all separated by insurmountable voids. And that leads to a sobering philosophical conclusion. If we cannot leave the solar system, then everything humanity will ever be must happen here. Mars, the moon, the asteroids, the icy moons of Jupiter and Saturn, these are our frontier. They are difficult, dangerous, and expensive, but they are reachable. With enough time and technology, We could build cities underground on Mars, research stations on Europa, mining colonies in the asteroid belt, and habitats orbiting the sun. But beyond that, there is nothing for us. Alpha Centauri might as well be in another universe. That realization changes how we think about the future. It means there is no escape, no backup Earth, no distant planet waiting for us if we ruin this one. Climate change, nuclear war, ecological collapse, and uncontrolled artificial intelligence are not just threats to our civilization. They are threats to the only civilization we will ever have. Some people find this depressing, but there is another way to see it. If this solar system is all we get, then it becomes infinitely precious. It is not a temporary home. It is our entire cosmic inheritance. We have billions of years of sunlight ahead of us. We have enough matter and energy to build a civilization that could last longer than any empire in history. But we must take care of what we have. And yet, a fair question remains. Could all of this be wrong? In the final part, we will confront the possibility of new physics, warp drives, wormholes, and whether anything could ever break the cosmic prison that separates us from the stars. At this point, the most obvious question is staring us in the face. What if all of this is wrong? What if physics has a loophole? What if one day we discover a way to cheat the cosmic speed limit and open a path to the stars? After all, history is full of experts who were certain something was impossible and were proven wrong. People once believed heavier than air flight could never work. They thought splitting the atom was fantasy. They dismissed space travel as nonsense. So maybe interstellar travel will eventually join that list. But there is a crucial difference between those old mistakes and what we are talking about here. Those past predictions were wrong because they underestimated technology. They did not violate fundamental laws. Airplanes do not break physics. Nuclear power does not break physics. Rockets do not break physics. They simply exploit laws that were not yet fully understood or engineered. Interstellar travel is different. The obstacles here are not technical. They are built into the fabric of reality. The speed of light is not just the speed of photons. It is the maximum speed at which cause and effect can travel through spacetime. Energy conservation is not an engineering problem. It is a rule the universe enforces everywhere, always. The distances between stars are not something we can shrink with better engines. They are part of the geometry of the universe itself. What about wormholes? What about warp drives? What about bending spacetime so that we move faster than light without technically breaking the light speed rule? On paper, general relativity allows these ideas. You can write down equations that describe shortcuts through spacetime or bubbles of warped space that carry a ship faster than light relative to the outside universe. But those equations come with a catch. They require something called negative energy, exotic matter with properties unlike anything we have ever observed. Not just a little negative energy, enormous amounts, more than all the mass energy of planets, more than quantum physics appears capable of producing. Every serious analysis shows that these concepts demand forms of matter that almost certainly do not exist. Warp drives collapse under their own contradictions. Wormholes require stabilization that violates known quantum laws. Faster than light signaling leads to paradoxes that break causality. In other words, the loopholes are mathematical, not physical. Could there be new physics that changes everything? Possibly. Quantum gravity, extra dimensions, or unknown aspects of spacetime could surprise us. But hoping for unknown physics to cancel known physics is not a plan. It is wishful thinking. Everything we do know points in the same direction. The stars are too far away. So where does that leave us? It leaves us here, in the solar system, with a vast but finite playground. Billions of asteroids, dozens of moons, Mars, Europa, Titan, and countless other worlds waiting to be explored. Enough sunlight to power a civilization for billions of years. Enough raw material to build habitats the size of continents. We do not need other stars to have a magnificent future. We need to understand and protect the one we already have. Science fiction trained us to imagine a galaxy filled with human colonies, starships, and alien empires. Physics offers a quieter, more profound vision, a single system, slowly filled with intelligence, creativity, and life, glowing around one star for eons. And maybe that is not a tragedy. Maybe it is a responsibility. Because if this is all we get, then every choice we make here matters more than we ever imagined. Every ecosystem, every technology, every decision about war, peace, and the future of our species. We are not meant to escape the universe. We are meant to understand it and to survive within it. The stars will always be there, shining on us from afar, reminding us of how vast and mysterious reality is. But this small, warm corner of the cosmos, this is home.